Hello and welcome to Mr. Jackson's chemistry class. Today we're going to talk about states of matter. So states of matter is a pretty simple subject, but we're going to get into some detail on what pulls things into different states of matter. Why does water exist as a solid, liquid, and gas? I mean, we can raise the temperatures and change that, but what? What are we fighting? What does the temperature do? Okay, so let's talk about a solid. A solid is a material that is highly ordered. The atoms inside are very closely packed to each other. There is a definite shape and a definite volume. Okay, so that's what we want to remember: definite shape and volume. Then we have a liquid. A liquid, we have a little bit more freedom. The materials are moving around. They will stay in the container, but we know that they can move and change around. So there's a little bit more randomness. So they don't have a definite shape, but they still have a definite volume. So we have a definite volume because if you poured 10 milliliters of water into another container, it'd still be 10 milliliters. So we have a definite volume, but no definite shape. Okay? That means it can change the shape of the container you put it in. So, but there's little bit more freedom. There's a little bit more space between the particles than there are there. Then what's a gas? A gas is when the particles are so random and so free to move that they will actually go and just go everywhere. So there is no definite shape, because we know if you spray some gas or a cologne or whatever in a room, it'll keep going and spreading out forever. So no definite shape or volume. It will just keep going and spread out, and pretty soon you won't smell that perfume anymore, or the cologne or whatever you spray. So there's just no attraction, and there's just complete randomness. So each state of matter has basically a different idea of how the atoms work together and they arrange and attract themselves. So we're going to say high attraction, still quite a bit of attraction, and almost little to no attraction. They're not even attracted to each other. They can just keep going farther from each other and not really even care. Okay? So why are the solids and liquids different from gases? Because there is more attraction between the particles. And we're going to talk about that today in this teaching. So there's more attraction. Remember, that's what things bond together. Well, there's an attraction between these particles. They are attracting each other. They want to stay next to each other. In fact, so much that in a solid, they'll never move from their position. Here there's an attraction, but that attraction is not as strong. They're willing to move around, but they'll still stay so far from each other, and this has little to no attraction. So how are the solids and liquids different from the gases? There's more attraction between the particles in a solid and liquid, but there is roughly almost no attraction in a gas. Okay, because they do not care to even stay close to each other in gases. Okay, because they'll just keep going and spread out and keep going forever. Okay, so fill in the following chart, give a proper name for each phase change. Okay, and we're going to identify them as endo or exo. So we know that when a solid turns into a liquid, we are melting. Okay, and when it's melting, this is endo, because what's happening is it's absorbing energy. Here, if we take the liquid and turn it back into a solid, we want to give off its energy. So this would be called freezing. Okay, that's what we use. But it's also sometimes called fusion in science, meaning the atoms are being fused together into this liquid, this solid state. Okay, and this is exothermic. Okay, so if we take water and we want to turn it into a gas, we've got to add energy in. So let's put our arrows here so I know what I'm talking about. If we add energy, we turn it in, we call this boiling. And you would want to put energy in, so that is endo as well. Okay, so that's boiling. Okay, sometimes called vaporization. Okay, so sometimes that's called vaporization. We're turning it into a vapor. But if you turn steam back into water or a gas back into a liquid, we call that condensation. or to condense. Okay, and to condense, you have to get that gas to cool down. And so when you get it to cool down, you have it releasing its energy. So this is exothermic. Okay, so to go to a higher state, it is endothermic. You got to add energy. To go to a lower state, you have to take that energy away that it had, and that would be exothermic. Okay, but can we go from a solid to a gas and gas to a solid? Yes, we can. You ever look on your car windshield on a cold morning? You walk out and you find frost. Okay, so you've gone from a gas back to a solid, because where'd that frost come from? It didn't rain that night, it didn't snow that night, so that frost came right out of the air. It was water in the air, touched the cold windshield, and then just froze right to the windshield. And so we call that deposition. It just deposited. And so the gas had to lose its energy. Remember, to a lower state, it is exothermic. How about a solid directly to a gas? Sure. You ever notice how the snow just seems to disappear? Not just melt, but it's been cold and freezing out every day, but yet the snowpack is getting smaller and smaller, because solids can just evaporate. How about mothballs? They just basically evaporate. There's no liquid left behind. And so dry ice does the same thing. Dry ice goes from a solid to a gas. That's to sublime. To sublime means go directly from a solid to a gas, and that would need to add energy. So that's endothermic. So these ones are endo on the inside, and these ones on the outside are exothermic. Okay? So I want to talk about those really quick. Okay, so now I want to go on and talk about, well, we have to add energy to pull these particles apart. They have all this energy. So that's what we're talking about. The whole goal on this discussion is about talking about the energy that's found in between particles, not inside, but in between, and that's what we have to overcome to change these states of matter. And every change in state of matter has a specific name given to it. And each change, either the energy comes out or energy goes in to make that change, okay? So solid to gas is sublimation, okay? To sublime, or sometimes sublimination, okay? Sublime, sublimination. Maybe that would be a better word. I forgot. I usually use the word sublimination, okay? Now, let's talk about bonds. We know what a covalent bond is. We learned that in Chemistry A. It is a bond where they share, but this one is polar covalent, so it is unequal sharing. And what does that mean? We have an atom like water, and what happens is you got the oxygen atom, and the oxygen is sharing with the hydrogens, but the hydrogens don't get to share the electrons as much. They're mostly over here on the oxygen, because the oxygen is pulling those shared electrons more that way. And so if the electrons are over here, you start to develop a negative side, and then these become slightly positive because their protons are being exposed. Okay, so it's unequal sharing, and so what happens is you get a charged molecule that's not fully charged like an ionic one, but what happens is the molecule is now starting to get sides that have kind of a charge on the sides. So water actually has a charge on one side and a charge on another that's opposite. It's kind of positive on one side of the molecule and negative on the other. Okay? What is an ionic bond? An ionic bond is when an atom actually just donates its outer electrons and becomes positive because it doesn't want it anymore, and it transfers it to another element that then becomes negative, and so it takes the electron into its shell. They're doing this so that they can actually have that stable octet. So this one is a transfer, and so they have a full charge, whereas these have a symbol, looks like a little symbol like that with an S with a little loop in the bottom. That's called a partial charge. It's not a full charge of an electron. And this side is partially positive on this end. So that's what the symbol means. It means a partial charge, where these have given away the electron. They've transferred the electron. Okay, so this is a transfer of electron. And so they have a full positive and a full negative charge. Okay, and this is where it leads me to in number 5. What is an intermolecular force? Okay, when these things transfer or unequally share, these charges like each other. They pull together. And an intermolecular force is when an atom, let's just draw this water. So here's this water molecule. It has a negative end and a positive end. It's got a partial charge. Well, it loves another water molecule, but the water molecule will flip around and it will attract to its positive end, like that. And so that's what they're doing. And so over here would be another water molecule that would be attracted to its positive and opposite charges attract. So an intermolecular force is an attraction between two particles that pulls them together. And if they pull real tight, you'll find them in a solid state. If they pull just a little bit, or strongly, but not too strongly, they'll be found in a liquid state. But if there's no attraction between the particles, they'll probably be found as a gas. Okay? And so intermolecular is the force between the molecules. So this is between. Okay? And so I just drew polar in the water. So here's water being polar attraction. And if you put another water molecule right here, like this, what happens is it will flip and it'll put a negative side near the positive side, and then it will start drawing more attraction. And so water is all attracted, but it's still molecules they can pass around between each other and let go of each other and still have something around to attract. Okay? So inter means between the particles or atoms or molecules. Between particles or molecules. Okay? And then the word intra means inside of the molecule or particle. Okay? So here we have sodium that has given away an electron. It is positive, is attracted to the chlorine, which took on the electron. Okay? And that is what's inside of the salt particle. So it's an inside bond, okay? So in here we have a covalent bond, but that covalent bond creates outside forces called intermolecular between the molecules. This one's inside the particle or molecule. So one's between, and that's okay. So the best way I can explain it is, let's say that I have these pieces of paper, okay? And here's these two pieces of paper. And there is atoms inside, and there's bonds holding these paper together. But then there's an attraction right here. So now there's an attraction by this glue between the pieces of paper, but then there's also bonds inside the paper. So one's between and one's inside, if that helps at all. Okay? So we have to understand there are intramolecular and there's intermolecular, between and inside. Okay? You need to know the difference between those two types of forces, because I'm going to use these ideas to explain how we have these. So when we talk about why atoms pull together and form different, more complex and tighter states of matter, these are formed because there are extra intermolecular forces. Okay? And these extra intermolecular forces pull the molecules tighter together. If there's no extra force, there'll probably be a gas because they really don't want to pull together. Okay? So if I want to get water to turn into a gas, I've got to fight these forces of water. And that's the reason why you've got to add heat. So if these particles vibrate so fast, they don't care about that attraction, and they're willing just to run away and be a gas. But if those gas particles slow down and lose heat, they'll find another water molecule and stick together. And that's what happens in the atmosphere. These particles have been heated up in the sun and they run away into a gas, but then as they go up in the atmosphere, they slow down and they run across each other. And when they stick to each other, they turn into a water droplet and then fall to the ground. And then if it gets cold enough out and they lose even more energy, they'll pack together and form ice. So we can change the temperature. So energy is what causes these things to be able to fight this attraction energy of intermolecular attraction. Okay? So let's move on and finish up our discussion here. Hopefully that helps. What are some unique characteristics? One of the unique characteristics, as we can see about water, is water has surface tension. You can see spiders that walk on the water because the water particles stick together so hard that little spiders can walk on the water. Okay, and so we also have like syrup, and syrup has a high viscosity, and so it flows really slow. Things that have a lot of attraction for each other. Okay, sometimes you see capillary action. So if you ever see this one would be in a graduated cylinder. Okay, we see that water pulls up the thing, and we read at the bottom of the curve, this area where it pulls up, that's called capillary action. So water has an attraction for the glass. So that would be capillary action. So those are 3 unique behaviors of water. Okay, also things are solubility, if you want to put that down. Specific things that will dissolve, okay? So, or solubility, or also another good one besides solubility is electrolytes. We'll talk about that one too this week. Electrolytes, meaning they can conduct electricity. Okay? So, what are 2 powerful intermolecular forces between ones? Well, I know I said ionic bonds were intra, but also if you're watching, the sodium, which attracts its chlorine, that's the molecule that's inside, that force actually acts on another chlorine and another chlorine and another chlorine around, which acts to another sodium, which these right here are in their molecules, but they still attract outside. So ionic bonds act inter and intra. And so they act inside and out. And so this attaches to that sodium, which they're in this bond, and then these act to this chlorine, which acts to that one. And so what happens is it keeps going on over and over and over again. So not only is one molecule attracted to itself inside, ionic bonds also act outside. So that's the reason why when you have ionic bonds, a lot of those materials are mainly found in solids. Okay? So weaker ones would be the polar bonds, so water molecules which have a positive and negative end, which we'll demonstrate in class, they like to form liquids, mainly form liquids. Okay, because it's more attraction rather than being a gas, there is some attraction, and so they pull together and they will attract each other. So we call that a dipole. The word di meaning 2 poles of charge, 2 polar ends. So that's what it means. The word polar means opposite-ended. So water is a polar bond. It's opposite-ended. It has a positive side and it has a negative side. And that's the reason why water is so unique. It's why we see surface tension. It's why some spiders can walk on water and that kind of stuff, because they can't, their weight does not push the molecules apart. They push together so strongly that the spider can actually stand on 2 water molecules and not fall into the water. Okay? How is boiling related to intermolecular forces and atmospheric pressure? Well, boiling is related to intermolecular forces is to get separation into gases, you need to add energy. And when you add energy, they vibrate so quickly that then as they vibrate, right here, I just guess I'll use this, they vibrate so quickly they can then pull away from this extra attraction. So boiling depends on how hot you have to get it, depends on how much traction. If there's a lot of attraction, that material might need to go way up into high temperatures to get them to finally separate and turn into a gas. Okay? And well, how about atmospheric pressure? What is that? Well, atmospheric pressure is the weight of the air. And air has a ton of weight. Okay? What happens is we have all these particles of air molecules. In that air we have nitrogen, oxygen, carbon dioxide we breathe out, and water. And as you look in the air, as you are lower in the atmosphere, the air's weight is really heavy the lower we go. So down by the sea level. Okay, I'm sorry, even below sea level. But if you get to sea level, you have less air on top of you. And if you go up in a mountain, you have just a little bit of air. And so the air's weight changes depending on where you are. Have you ever dove into a pool? The deeper you go into a pool, the deeper you end. You'll notice that your ears feel different in the pool. As you go deeper, you can feel the pressure of the water on you. So the deeper we go in our atmosphere down towards the earth, there is more weight on top of you. Well, that weight is what sits on top of a pan of water. So not only does the water in here to boil have to overcome this attraction, but it has to overcome this weight of the air pushing down, keeping those molecules together. So actually, as you go up in a mountain, water boils at different temperatures. So the water would boil maybe down here, but at sea levels where water boils at 100 degrees. But if you go up in the mountains, your water may only boil like at 85 degrees. Okay, depends on how high you go. If you go below the sea level, let's say in a cavern, it might boil at 105 degrees Celsius. So the water can boil every day at a different temperature depending on how much air is on top of you or where you're at in the world. But every day the air temperature and pressure changes because we have gases like water is 14, nitrogen is 14 plus 14 is 28 grams. 16 and 16 is 32 grams. 32 plus 12 more is 44 grams. And then the formula weight of water is 18 grams. So on days where there is more moisture, what happens is more moisture means more water or more humidity in the air, which is water. The air is lighter because what happens is you push something that weighs only 18 and you push this air out, and so the air actually gets lighter on humid days when a rainstorm comes in, and so there's less pressure. Then if there's less pressure pushing down, water boils at a lower temperature. So that's the reason why when I did an experiment in another class, it actually the boiling temperature was only like 97 one day. Some days it's 99. Some days it's 100. It all depends on what the air is like. And so when the air gets dry and storms move out of the area, this moves away. Then these other airs come back in. The air weighs more, and so the boiling point goes back up. So on dry days, the boiling point's higher. Okay, so that's what I wanted you guys to know about gases and why states of matter and how they're created, okay? So I need you to know these ideas about why things have some intermolecular and intramolecular and how they help create these different states of matter through greater and less attraction. Less attraction, more attraction, but still enough room to move around, and a great amount of attraction where they actually get so close they form a tight arrangement, okay? So those are the purposes and the ways states of matter are created. Okay? Thank you for joining me. Have a great day. God bless.